All right, class, I'm going to continue with the lecture for 1.3. And just to kind of remind us where we're at here, right? So this one, let me kind of make this a little bit. Okay, that's a little better to see. All right, remember how we used to graph this right here in class? So we graphed it in stages, right? X squared is the main function that we're looking at. We have a negative in front of it, so it's going to have a reflection about the x-axis. And then you have this little 1, which this little 1 acts as a vertical shift going up. So now the vertex here is at 0, 1. All right, trig functions do the same. The basic sine curve goes with the maximum of 1, negative 1 is the minimum, and it takes 2 pi to make 1 full revolution. So what happens if you have a 3 on the inside of this? It shortens your period, is that right? So instead of going all the way to 2 pi, now we only go to 2 pi over 3. That shortens the period. Half of that would be pi over 3. So that's good. And then the last part right here, 4 sine of 3x, means you're just going to go up 4 units and down 4 units as the max and the min, respectively. All right, let's keep on going. This one, I think we stopped on this one as we did it here. So y is equal to 1 over x minus 4. That is a reciprocal function. The basic one is right here. And then what happens with the minus 4 over here? It just scoots over to the right. Remember, the minus 4 is technically inside the function. So because it's inside the function, it scoots over to the right. If we had a plus 4 or minus 4 on the outside of this, then we would have been going up or down vertically. Okay, and the next piece that we'll encounter, and in calculus we have to think about this here, is a graph that looks like this. So you have absolute value of a function inside something. Why do we do this? Because sometimes, well, a lot of times if you're dealing with concrete objects, you don't go into the negative of something. We stay positive. That's kind of what we're looking at. So because of that, absolute values guards us from going to the negative values. All right, let's go with it here. So how do we graph this, which is going to be a little bit unusual. Do you guys notice this is a parabola though? All right, parabola, and then what we do is we just isolate the parabola itself, x squared minus 2x. And then, do you guys remember something called completing the square? What we do is we figure out what we need to add right over here. So we take this guy, we divide it by 2, and we square it. And whatever to do add inside the parenthesis, we're going to subtract outside the parenthesis to balance it out. And then we are going to write the binomial form of that perfect trinomial. Done. So what we have here, we're trying to make it look like this. That's the whole point here. This is the graph of a parabola. All right, and the vertex, once you get into this form, the vertex is HK. All right, so let's graph this guy. We have a vertex at, oh, okay, the vertex is at negative or 1, negative 1, right? But don't forget we have the absolute value here. So let's talk about that in just a bit here. So if it was just a plano graph, we have a vertex of 1, negative 1. And that's what's called the vertex form of the parabola or graphing form. That's what we're looking for. But we want to take a look at just a couple of more values if we could find. All right, so back to the original graph. The original graph was like this, without the absolute values. What would be the y-intercept here? Remember, plug in a 0 here, plug in a 0 here. It's y is equal to 0. Perfect. And then what we want to do is we want to figure out what are the x-intercepts. And so notice we can factor this form out. Is that right? Factor this form out. X goes on the outside, x minus 2 on the inside. And notice what are going to be the zeros for y here. If y is equal to 0, that means x is 0 and x is 2. Based upon those points, what we have is we have x-intercepts. There's two of them, 0 and 2. Okay, so I got my vertex, I got my y-intercept, I got my x-intercept. As long as I have those, I have at least a good rough idea of this graph. That's what I want. So let's go for it here. So it looks like this. So let's see, I got my vertex at 1, -1. Got my zeros at 2, 0, and 0, 0, and then it's also my x-intercept and my y-intercept. All right, are we good there with my original graph? All right, that is a parabola. Okay, except the only thing is it's missing the absolute value. So this little piece right here, just right at the x-axis, what we're going to do is we're going to just take that as the reflection. So notice right here, it's going to be the same thing. We're adding in the absolute value now. We hit the 0, 0. We hit the 2, 0. Now 1, -1 is going to jump up to 1, +1. And notice, as long as it's above the x-axis here, it's mimicking the same graph right here. So that graph there. But once it goes below, we want to reflect that, just that piece above the x-axis. And then it becomes the same exact graph. So there it is. We reflect only the pieces that are the negative y area. Okay, so that was the last of the graph. So let's move on to the good stuff called composition of functions. There it is, composition of functions. Okay, so find the functions f composed with g, g composed with f. Then we're also going to do f composed with f, and then we're going to do g composed with g. Whoa, and then also we've got to take a look at our domains. Wow, okay, let's take a look at this stuff. So notice that f, yeah, f can be composed with g, that's easy. We can go the other way with it if we like, and we can compose functions inside each other. All right, so let's go for it here. So a. All right, I'm going to write it here a couple of different ways. So f composed with g. Technically, the way it's written is this. The g function is actually inside the f function. All right, and a good way to write it is you just write what the g function is. So the g function is x squared plus 3x plus 4. And here's what we're going to do now. We're going to stuff the g function into the f function. So we're going to start writing the f function. When we get to x, we're going to substitute all that stuff in for the x. So here it goes. F of x is actually x minus 2, so it's just going to be x squared plus 3x plus 4. Just that's this piece right here. Make sure I'm going to laser pointer. So this guy here is this one right here, right? And minus 2. So it's almost like this. You're going to take this right here, and you're going to stuff it into this function here. All right, so what happens if you go the other way? Oh, that's right. We do have to simplify here. And how about a plus 2? Okay, let's go the other way for b. This is g of f here. So g of f. And so what we do is we say now f is actually sitting inside g. All right, what is the f function? The f function is x minus 2. So notice the g is still on the outside, right? G is not multiplying this. It's the function g of x minus 2. So here it is. We're going to start rewriting the g function. When we see an x, we replace it with x minus 2. So let's go with it here. So this is x minus 2 squared plus 3 times x minus 2. And then it's a plus 4. All right, do we need to simplify this out? Yes, technically we do. So x minus 2 to the second power. This probably you should know. Kind of quickly do. If you need to FOIL it all out, that's fine. There's like this little quick way of doing it as well. All right, so x squared minus 4x plus 4 if you did it correctly. The second part was the 3 times x minus 2, which makes negative, or sorry, positive 3x minus 6 this time, and a little plus 4 right at the end. And the question is, can we combine any like terms? I think so. X squared is over here. A negative 4x and 3x makes a negative x. And then how about a 4 minus 6 plus 4? That would make a plus 2 done. So there's our final answer of G composed with F. All right, let's take the next one here. C. This one we're going to compose F with F. And this was actually a good one to sort of think through here. Let me see if I can. Notice what F does real quick here. This is x minus 2. What does F do? It subtracts 2 from our function. It makes something 2 less. We good? So now the question is, what happens if you combine these two functions together? What would it do? What would subtracting 2 and then subtracting 2 again make? Some of you guys probably would have guessed it already by now, but let's go with it. So F composed with F of x. That's another notation. Those all notations are very similar. That means the F is sitting inside F itself. So let's go for it. Let's do the inside F here. The inside function is F minus x minus 2. Okay, we're going to rewrite F. When we see an x, we replace with x minus 2. So it'll be x minus 2 minus 2. And it would be, oh, okay, hold on. So if you do F twice, right, if you subtract 2, you subtract 2 again, if you want to write it as just one single function, that's what composition function does, writing the same thing as one single function, it becomes x minus 4. That made sense a bit there. All right, and now the tough one. What happens if you want to compose G with G? Whoa, okay, so let's see, G composed with G of x. Again, that's just another way of writing it. And this one also is another way of writing it, G of x. All right, so let's do this here. We're going to rewrite the inside G as its own function. So this is going to be x squared plus 3x plus 4. All right, so now we're going to start rewriting the G function. Each time we see an x, we replace it with x squared plus 3x plus 4. Let's go with it here. So this would be x squared plus 3x plus 4 to the second power plus 3 times x squared plus 3x plus 4, and then plus 4 at the end. So notice it's the G function again sitting inside itself. Okay, if you need to take some time to multiply this out, go for it here. So x squared plus 3x plus 4, we're going to FOIL all that out because of that 2 there. All right, so let's go with that. Let's see, let me isolate this just for a second here. So it's going to be this one plus another one just like it. This one we actually can already distribute here. So 3 to the x squared, to 3 to the 3x, and 3 to the 4. And then don't forget this little plus 4 at the end. Okay, this is the tough part right here, just foiling all of this out. And so let's go for it here. So here it is, x squared times x squared, x to the 4th, x squared times 3x would make 3x cubed. X squared times 4 would be 4x squared. Okay. First iteration is done. Let's keep on going. Now we move to the 3x here. So 3x multiplies everything in the other parenthesis here. So 3x times x squared is 3x cubed. 3x times 3x is 9x squared. And 3x times 4 is 12x. Perfect. And the last one here, just the 4. So 4 times the x squared. 4 times 3x. And 4 times 4 is 16. All right, don't forget we still have all the other stuff over here too, right? So we still have plus 3x squared plus 9x plus 12 plus 4. Okay, I think I have just enough room here, but I think my video cuts it off right here at the bottom. So I'm going to say it, and hopefully we see a good portion of it here. So the final answer, right, we start off with the highest power for x's. So how many x to the 4s do we have? Just that. So how about, oh, you guys don't see it here, it's below the video here. So there should be an x squared right over here. I'm sorry, x to the 4th here. Right, how many x cubes do we have? So there's 3x cubed here, another x cubed here, so just 6. So plus 6x squared. Again, it cuts off, that's like a 6 right here. X squared. X cubed, sorry, x cubed. X squared is now 4. There's 9 here, and then there's 4 more here. And there's 3 right here. So it's 4, 9, 4, 3. 13, 17, 18, 19, 20. So 20x squared. So 20x squared is there. Now single x's here. So I got 12x, another 12x, and a 9x. So 12 plus 12 is 24. 24 plus 9 is 33 x squared. Or just x, sorry, just x. All right, and the last one. Let's see, I need, oh, there's a 16, my constant term, my 16, my 12, and 4. So if that's the case, we get ourselves 32. That was a toughie. That was g going into g, really a quadratic equation going inside itself. That's crazy. Okay, so now the question is this. Can we do 3 functions? Absolutely. Never done that before in algebra class, but let's go for it here. Can I do 3 functions going inside themselves? Give you a little bit of time to write that down. I have the f function, I have the g function, and I have the h function. All right, let's see. Let's rewrite this so it's more of notation here. So that turns into f of g of h. And almost like we're going to go from the inside to the outside. So h is 1 minus x. So f stays here, g stays here, but h, we're going to give the condition form of h. All right, that's good. So now next thing. Now I'm going to now stuff h into the g function, right? And the g function, what that does, it squares things. So in this case, it's going to be f of squaring that piece. All right, what does the f function do? It doubles whatever it wants, whatever it has, and then subtracts 1 from it. So it doubles and subtracts 1. So let's rewrite this one as doubles and subtracts 1. And that is it. I don't think you need to reduce those anymore. I think that's just the correct answer. All right, let's go with it. Come on. All right, so then let's go a little bit backwards here. So if this was this capital H of x, if that was a function that had 3 functions sitting inside of themselves, think about what are the 3 functions. What's the centermost inner function? What's the next level function? What's the highest level function? So it's just making you think about functions themselves here. So I notice an 8th root here, right? That's one function I see. That's the topmost function. Then I also see this little 2 adding the absolute value of x. So I'm going to do this. I'm going to say that guy right there is the most inner function right here. The most inner function is absolute value of x. Okay, if that's the case. Then the question is, what's the next level? The next level is what is being done inside the 8th root. So in this case, remember this guy now has to just be a regular x, is that right? So g of x would just be 2 plus x. All right, and then the main function, notice it's the cube, sorry, not cube, 8th root. 8th root of whatever is inside there. So that has to be the top function. The f function is just the 8th root. Right, hopefully that makes sense. We are combining functions like little nesting dolls, and we are making sure we can still separate them out. All right, this one is just one. It's one of these problems. I thought it was kind of a good problem to sort of think through. Do you guys first remember what in the world is an even function and what is an odd function? Even functions are something looks like this. It just means it has an even power. That's it. Something is called an even power function. X squared is considered an even function. And g, it has to be an odd function. This means it has an odd exponent for your power. So now the question is this, what can you say about, oh, and look at that, this is not composition of functions. This is multiplication of f and g. All right? So let's go for it here. So the multiplication of f and g can be written like this, right? It was right here. Just if they're just by themselves, letters by themselves mean say multiplication. Right? All right. Sometimes it's f of g with an x because it goes with the variable here. All right. And then the way we actually write it out would be like this. It's supposed to be f of x with a little dot between that and g of x. So now let's put in our functions here. F of x is x squared. Or g of x is x cubed. And remember, whenever we multiply functions together, all we do is we add the exponents. Add the exponents. What kind of function is f to the 5th power? Even or odd? Okay, so here it is. So suppose one's an even function, one's an odd function. If you multiply them together, you will produce an odd function here. So it will be an odd function. Okay, that's just, it's kind of a little bit of a abstract problem to sort of think through. You got that one great. All right. So I'm going to stop lecture. That is the end of this section here, and you guys will have some time to do homework. All right, and enjoy the rest of your day.